next presentation. It's going to be the last presentation of this session. This is Mr. Justyna Niewiadomska-Kaplar from Italy, Scientific Publishing House, Rome. She's going to speak on new approach to the molecular electronics of fluorography. Interesting thing is that she has also contributions apart from material science. She has contributions in music, history of arts, and so on. Okay, Justyna, welcome you.
Yes. I would like to thank the organizer for inviting me also this year. This is presentation of a theoretical model which describes chemical bonds and other structural aspects of the compounds. This model is called the ID model, from words ingegneria in Polish or ingegneria in Italian, words that mean engineering and design, ID. The second thing what I was to say, when I refer to the distribution of electrons in space, I am dealing with statistical simplifications. And last one, in this presentation, and I will always report to the fluorographene C2F chair or graphene half fluorinated in the single side. This is summary, generic comparison of the structure of graphene and fluorographene between the quantum mechanical model and the ID model, brief description of the fundamental theoretical elements of the ID model, description of the distribution of the electron cloud of carbon and fluorine in both model, description of the chemical bonds in fluorographene in the both model, and last one, analysis of the properties of fluorographene in the quantum mechanical model, ID model, and experimental data. This presentation can be considered an attempt to respond to last year's conference questions regarding the experimental confirmations of the proposed model and its quantitative aspects. For this, I start the presentation by citing a fragment of the article Structures of Fluorinated Graphenes and Their Signatures, they are the references, which state that relevant data reported in various experiments do not appear to agree with the properties calculated for any one of the stable fluorine structures. In this respect, imaging of fluorinated graphene surfaces by scanning tunneling and atomic force microscopy, as well as X-ray photoemission spectroscopy, is expected to shed light on the puzzling inconsistency between theory and experiment. So the authors of this article propose use of imaging techniques, therefore experimental techniques, to understand the inconsistency between theory and experimental data. In this presentation, on the other hand, a verification of the theoretical contribution is proposed. This is comparison of the structure of the ring plane between the quantum mechanical model and the ID model. This shows great differences. Also, every ring planes between this both model shows great differences. From the drawings, we can see that the bonds between the axial orbitals are similar in the two models. On the other hand, the bonds of the ring plane change radically. In the ID model, there are two ring planes, and carbon atoms have a dense reticulation of pi bonds at the level of the ring plane, which translate from a practical point of view into a significant increase in the force of cohesion between the atoms. Comparison of the structure of every ring planes between the quantum mechanical model and the ID model show that the structure of the fluorographene in the quantum mechanical model change completely compared to the graphene structure. Instead, in the ID model, the fluorographene maintains the structure of the graphene. I would now like to repeat the achievements of the description of the theoretical concepts of the ID model that for those interested are located online. This will be briefly summaries of ID model. The structure of graphene and fluorographene has been described in this research work by introducing some innovative elementary theoretical concepts, such as, firstly, interpretation of the electron pair not as a concentration of the electron cloud on one side of the nucleus, format lone pair, but electron pair are interpreted as a symmetric distribution of the electron cloud on both sides of the nucleus. Secondly, hypothesis that in the atomic elements from boron to neon, there are not two s orbitals, but the shell consists of the spherically symmetric orbital internal 1s and 3 on 4 bilobate orbitals 2p. Thirdly, hypothesis that in polar bonds and the majority of multiple bonds, one electron is shared, not an electron pair, and therefore distinction of intermolecular bonds in bielectronic and monoelectronic. Fourthly, interpretation of the transformation of geometry of molecules in relation to the number of the bonds as a result of changes in the spatial relationships between atoms and not as a result of the hybridization of orbitals. And last one, hypothesis that the formation of multiple bonds occurs thanks to the transformation of bielectronic bonds into monoelectronic bonds, where only one electron is shared. The result of sharing of a single electron in a bond creates the bipolar orbital, the positive part of which attracts electron. Intermolecular bonds, according to the ID model, they are synaptic bonding when there is direct contact between the orbitals. Non-synaptic bonds when there are not contact between the orbitals. Amphosynaptic bond, direct and lateral contact. Monoshared and polyshared bonds that generate monohyperconjugation. Mutual, non-mutual, and partially mutual bonds when an atom is donor and acceptor, or only donor, only acceptor of electrons. In the quantum mechanical model, there are 3 types of bonds in organic compounds. In the ID model, there are 8 types of bonds. The variety of bonds determines the variety of properties. In the ID model, the formation of tetrahedral, planar, and linear molecules is not due to the presence of 3 types of orbital hybridization, because the mechanism for creating different bonds is not to change the conformational geometry of individual atoms, but to change the spatial relations between atoms. The change of the spatial relation between atoms determines change in the spatial parameters of the molecules, so that these parameters can be predicted by applying trigonometric equations. Measurements made with the ID model are very similar to bond length measurements obtained experimentally, such as those of triplet ethylene, bond length, graphene, graphite, alkenes, and acetylene bond lengths. Now I want to show you one animation when we can see how the bonds of the atoms are shortened when they approach. This is ethane, this is triplet ethylene. This is situation of ethylene. This is bond length of benzene, graphene, graphite, alkenes, and acetylene. I would like to underline the calculation of the bond lengths between carbon atoms in the various stages of unsaturation of its molecules, because they are one of the experimental sources of this research and one of its quantitative aspects. In the quantum mechanical model, in the atomic shells developed thanks to the experimental data, hybridized excited states, 2 s electrons are missing. The structural variety of carbon compounds is explained through a theory of hybridization of the orbitals and introducing these distinctions between triplet and singlet states in all about 9 electronic configurations. To this number must also be added carbon not neutral states. In the quantum mechanical model, an orbital occupied by 2 electrons form lone pair. In the ID model, in the atomic carbon shells, there are not 2 s electrons, which is agreed with experimental data. They are 1s and 2p electrons. The electrons of the orbitals p are placed symmetrically from the 2 sides of the nucleus, so no lone pair are formed. The spared electrons p determine the polarity between the 2 lobes of orbitals. The structural variety of carbon compounds is explained as a change of spatial relationships between only 4 types of shells, including 2 paramagnetic shells, so including non-neutral shells. In the ID model, the shells of carbon atoms are found in the fundamental state in biomolecules, carbenes, carbonate, carboxylic, carbonate group. Carbon shells in excited state is in fossil hydrocarbons. The same situation we are for shells of fluorine. So carbon in quantum mechanical model has 4 possibilities of bond with adjacent atoms. In ID model, they has 8 possibilities. Fluorine has 1 possibility. In ID model, fluorine has 4 possibilities. So carbon has 4 points of contacts with adjacent atoms, with which form free bonds sigma and does not form bonds with the most distant atoms. Carbon sp3 binds with fluorine sp3 with the sigma bonds. The graphene ring is completely transformed since the carbon orbital sp2 are transformed into sp3. In the ID model, carbon atoms have 8 points of contacts with adjacent carbon atoms, with which shape 12 ties and also 3 other ties with the most distant carbon. Fluorine binds with carbon with an electron in the synaptic monoelectronic bond and with polyshared pi bonds. Structure of the graphene is therefore maintained, so fluorographene retains many properties of graphene. Free carbon atoms adjacent to fluorine become paramagnetic. Chemical ties determine the structure and properties of molecules. We can analyze properties of fluorographene according to quantum mechanical model. Fluorographene, it should not be stable because half of carbon atoms will be radical species. Fluorographene not having the pi bonds, it should not melt in the solvents where there are important quantities of pi bonds. It should not keep metallic properties of the graphene. It should not maintain the planarity of the carbons ring. Fluorographene having the completely different structure and bonds of the graphene, it should not maintain such mechanical and elastic properties. It should not maintain similar thermal properties. Au contrary, in the ID model, fluorographene, it should be stable regardless of the carbon and fluorine stoichiometric relationships. Fluorographene ID having the pi bonds, it should melt in the solvents in which there are important quantities of pi bonds. It should maintain metallic properties of the graphene. It should maintain the planarity of the carbon rings. Fluorographene having the structure and ties very similar to graphene. It should maintain such mechanical and elastic properties. It should maintain similar thermal properties. Now I want to talk about properties of fluorographene according to experimental data. For reason of time, I will make only the summary of the citations. So, half-fluorinated graphene is stable and show much better distillation in solvents with a large closed conjugated system. According to experimental data, elastic deformation of fluorographene is comparable with graphene. It's smaller but comparable. According to experimental data, G2F chair structure fluorinated on one side of graphene, it is found to be a metal. He exhibits metallic behavior. Between theoretical result and experimental data, there are discrepancies for the band gaps. Fluorographene chair structure is found to be metal. According to experimental data, the planarity and pi bonding of the graphene, it could be non-destroyed. The hyperconjugation among fluorine and carbon atoms produce only apparent destruction of the planar structure between the carbon atoms. Carbon-fluorine bonds are semionic, not that in the semionic bonds model, carbon orbitals are considered sp2. So carbon rings should be planar. In conclusion, it can be said that the ID model corresponds better with the experimental data than the quantum mechanical model. In the ID model, the fluorographene maintains the structure of graphene, and therefore, also its properties remain similar. Because the presence of the most hyperconjugated bonds in the ring plane allows to preserve the structural model when the axial electrons are engaged in the bonds with the fluorine. On the contrary, in the quantum mechanical model, only the axial electrons form the pi bonds. Therefore, when these electrons are engaged in the bonds with fluorine, the structure and therefore the properties of fluorographene must change radically respect graphene. Thank you very much.
Thank you. Thank you, Dr. Justyna. Thank you for the nice presentation. Interesting theory as well as experimental evidences. Thank you very much for the nice presentation.